Hi grade 12s. This video is the last video in the asymptotes kind of video series because we're now looking at mixed asymptotes. So if we're given a graph, which we're going to draw very shortly, can we figure out the asymptotes that they have? So far we've done a vertical asymptote, a horizontal and an oblique asymptote, as well as the fact that we've done removable discontinuities. So can we pick up all of these different things, because that's going to be a huge help when we draw functions in the next video. So let's have a look. Determine these asymptotes and the removable discontinuities of the following. And here is question A. Question A says x squared plus 5 divided by 4x plus 2. Well, first of all, I always check for vertical asymptotes first. My first port of call is, can you simplify? Because if you can simplify, if one of the factors on the bottom disappears, then you don't have an asymptote, you have a removable discontinuity. So that's my first question. In this example, I can't simplify. The bottom is factorizable, but the top isn't, and so there's nowhere I can go. So my next question is, do I have any vertical asymptotes? And don't forget that vertical asymptotes occur because there is a value for x that is not allowed to happen. And this is a denominator that I'm looking at, because my denominator is not allowed to be equal to 0. So if the problem disappears, as we've said, it's a removable discontinuity, but in this case, the problem didn't disappear. 4x plus 2, when that equals to 0, I will have a vertical asymptote. So that's when 4x is equal to negative 2, so when x is equal to negative 1/2. So that would be my vertical asymptote. Now, in an exam, they want you to be explicit about which asymptote each one is. They can't assume that you know that that's a vertical asymptote or a removable discontinuity. So you must be explicit. You mustn't just give the equation. Okay, so now we've checked off removable discontinuities. We've checked vertical asymptotes. Horizontal versus oblique. Now remember, you either have one or the other. You don't have both. Now, when do you have a horizontal asymptote? This is when the degree at the bottom is greater than or equal to the degree at the top. And when do we have an oblique asymptote? Is when the degree at the top is 1 more than the degree at the bottom. So that equals the degree at the bottom plus 1. So that's why these are completely different ideas, and so you either have one or the other. Now, if I look at this for a moment, this definitely has an oblique, because this is an x squared term, and this is an x term. So how do I find my oblique asymptote? Hopefully you enjoyed the last video, where basically I'm going to rewrite this x squared plus 5 as 4x plus 2 multiplied by something. So I say to myself, what do you need to multiply 4x by to get to x squared? Well, definitely an x, but I don't need the 4. So it's going to be a quarter x, or x over 4, same thing. Now don't forget that if this is an x squared term, what we said when we were practicing oblique asymptotes is that you need to be accurate to a degree 1 less than that. So I need to be accurate to the x term. Now, if I multiply this out so far, what is this so far? Well, 4x times by a quarter x is the x squared I want, but 2 times a quarter x is a half x. Now, that's not accurate. So because this isn't accurate, I'm not finished. So this is not accurate. So how do I correct that? Well, I need to minus a half x. So when I multiply 4x by something, it needs to be minus a half x. So it needs to be a minus. Definitely doesn't need an x, but I'm pretty sure this needs to be an eighth. Simply because now I would have 4x multiplied by negative 1/8, which is minus a half x when you simplify. And if I multiply 2 by negative 1/8, I'd get minus a quarter. So let's just complete our equation here, because this is not equal. This is now fine. That simplifies to no x's, x squared and no x's, but minus 1/4 is not right. So how do I go from minus 1/4 up to 5? Well, I'll have to be adding 5 and 1/4, because, or you could have said 21 over 4. But basically I need to add a quarter to get back to 0, and then add 5 to get to 5. So how does this help me? Well, all of this helps me because therefore I know my oblique asymptote. Pick a nice color. That over there is my oblique asymptote. So my oblique asymptote is at y is equal to a quarter x minus 1/8. I also know, if I look at my remainder, that my graph will not hit the asymptote. Now, that's not what this question asks, but that's really important when we're drawing graphs. So this graph will not hit the asymptote. Why? Because there's no ways that that remainder can ever be equal to 0. And so there's no ways that these graphs could ever intersect each other. Cool. Now, how much of this working would you need to show? Pretty much everything. You can do some of this in your head. So, for example, this you could do in your head if you wanted to. I like to think while I write, so it's entirely up to you. So, our steps were, can you simplify? Then we check for vertical asymptote, and then we check for oblique or horizontal, because you obviously can't have both. Great. Let's look at another one. G of x equals x squared plus 4 over x minus 2. So first question is, can I simplify? Now this is very tempting to simplify, because I see x squared plus 4 and I'm like, oh, maybe it's a dots, but careful, it's not a dots. So x squared plus 4 cannot simplify because it cannot factorize, and so immediately I can see that this will have a vertical asymptote. It will not have a removable discontinuity, and so my vertical asymptote is that x is equal to 2. Okay, so once I've checked my vertical asymptote, I say to myself, is there an oblique or horizontal? And this one is going to have an oblique because my top degree, my degree of my numerator is 1 more than my denominator. So how do I do that again? Exactly what we did in the previous question. Hopefully we start getting, really good at this. So this equals to x minus 2 multiplied by something. And whatever it's multiplied by is going to be my oblique asymptote. So x times what will give me x squared? This has to be x. If I multiply out what I've got so far this is x squared minus 2x. Now don't forget, you have to be accurate to a degree 1 less than the left-hand side. So I have to be accurate to the x term. This is not accurate. I don't want minus 2x. In fact, I want no x's. So I need a plus 2x to cancel this out. So if I put a plus 2 here, that will now give me the plus 2x I want, but it will also give me minus 4. Now, minus 4 is not what I want. Now, to be honest, in this particular question, I actually don't care what the remainder is. But when we go to the next video, I'm going to care about the remainder because it tells me whether I need to plot where the point cuts, where the graph cuts the asymptote. So if I'm at minus 4, how do I get up to plus 4? I need to plus 8. So I can see that this graph will not cut the oblique asymptote, but at the moment all I care about is what is this oblique asymptote, and this asymptote occurs at y is equal to x plus 2. So as x tends to infinity, this graph is going to tend towards that line. We will see that in the next video, and then it really comes to life when you can see all of the different ways the asymptotes work. Right, if I just scroll down to the next question, my first question always needs to be, can I factorize and simplify? Now this one looks pretty interesting. It's a quadratic over a quadratic, and so it's hard to see whether you can simplify without factorizing. So let's check. Definitely you can use your calculator to factorize, but personally this is pretty easy to factorize. It's x plus 2, x minus 1, and at the bottom here I've got x plus 5 and x minus 1. So what do you know? Can I factorize and simplify? The answer is yes, because this x minus 1 will cancel. So therefore immediately I know that there's a removable discontinuity, which means basically a hole in the graph, discontinuity at x is equal to 1. Simply because if x is equal to 1 is not allowed in this function, x is 1 is not part of the domain because the original function would be undefined. However, this limit would exist. And just out of interest, where will this removable discontinuity be? It'll be when x is 1, and I can figure out the y value, because if I put in 1, I get 1 plus 2 is 3 over 1 plus 5, so it's 3 over 6, which is a half. So at 1/2, there will be a removable discontinuity. Now, I didn't actually have to write that down, as long as you say removable discontinuity at x is 1. Okay, next thing is, are there any vertical asymptotes? Well, x minus 1 is no longer a problem in the denominator, but there is still a problem in the denominator, and that is x plus 5. So my vertical asymptotes will be, or asymptote singular, will be at x is equal to negative 5. So don't forget, when you write this in an exam, you must tell me what asymptote that is. So far we have a removable discontinuity and a vertical asymptote. And finally, I can see that I'm going to have a horizontal asymptote because the degrees are equal. So my horizontal asymptote, which is our first example for this example so far, because these degrees are equal, I can find the limit as x tends to infinity, and it'll work out to a constant. So what is the limit as x tends to infinity of x squared plus x minus 2 over x squared plus 4x minus 5? Well, I can pretty much see this answer because I noticed in the video, if these are the same degree, the limit basically just becomes a ratio of their coefficients, which in this case is 1. But if we want to just explain why quickly, because that's a bit of a shortcut pattern type method, basically you divide the top and the bottom by the highest exponent of x. So this basically becomes the limit as x tends to infinity of x squared divided by x squared is 1, and this becomes 1 over x. Now, why do these no longer matter? Well, 1 over x is going to be 10 to 0, and 2 over x squared is going to tend to 0. So this is 1, and 4 over x is going to tend to 0, and 5 over x squared is going to tend to 0 as x tends to infinity. So this limit just becomes 1, which means my horizontal asymptote is at y is equal to 1. So I shouldn't say at, I should say is y is equal to 1. So my horizontal asymptote is y is equal to 1. So if you don't want to show working, it's acceptable. I personally, if this is my exam, I'd show that working, just in case. You never know what the memo has on it. Right, soldiering on. This is going well. Question D. F of x equals 4x plus 2 over 5 minus 3x. Can I simplify? Well, this is a linear over a linear, which means unless there's going to be a common factor on the top and the bottom, I can't cancel anything. And I don't think the top can factorize, but the bottom can't. And so there's no way this can simplify. So the answer to this was no, which means there's no removable discontinuities. However, there is a problem in the domain. So where does 5 minus 3x equal 0? So 5 would equal 3x. So x would equal to 5 over 3. That will be a vertical asymptote because that will not be allowed as part of the domain. Okay, and so finally, do I have a horizontal or an oblique asymptote? I'm going to have a horizontal asymptote because the degree on the top and the bottom are equal. Horizontal asymptote. So I'm just going to write myself a note here, because the degree is equal on the top and bottom. And I know that if the degree is equal on the top and the bottom, basically the asymptote simplifies down to the coefficients of the x's. So I'm pretty sure that this is going to have a horizontal asymptote of y equals negative 4 over 3. But let's check. What is the limit as x tends to positive or negative infinity of 4x plus 2 over 5 minus 3x? Well, basically I divide by the highest exponent of x, which in this case is x. So if I divide the top by x and I divide the bottom by x, I'm effectively dividing by 1, which is why I'm allowed to do this. So 4x over x becomes 4. 2 becomes 2 over x, which means it'll tend to 0. 5 over x will tend to 0, and this is minus 3. Now, both of these tend to 0 as x tends to infinity, and that's why you get negative 4 over 3. So therefore, my horizontal asymptote, if I just change color, is at y is equal to y equals negative 4 over 3 is the horizontal asymptote. Don't forget to tell your examiner what asymptote you are expecting that to be, because otherwise they can't assume that you knew. Great. Couple more to go. Let's look at E. G of x equals x minus 3 over x squared minus 2x minus 3. First, very importantly, can you factorize and simplify? Now this looks promising because x minus 3 might be a factor at the bottom there, so let's check. If I factorize the bottom, I indeed do get x minus 3 and x plus 1, which means I can cancel this factor. So therefore, there is a removable, unless I've made a mistake here, I'm pretty sure there is a removable discontinuity at x is equal to 3. Great. So I still also have a problem at the bottom here, because x plus 1 means that x is equal to minus 1 is a vertical asymptote. And so lastly, do I have a horizontal or an oblique asymptote? Now here my degree is bigger at the bottom, so therefore I have a horizontal asymptote. So a horizontal asymptote of, and this is going to be y is equal to something. Now I can pretty much cheat here and realize that if the degree is bigger than on the bottom, you always get y is equal to 0 as your horizontal asymptote. Because what is the limit as x tends to infinity of x minus 3 over x squared minus 2x minus 3? Now just out of interest, this simplifies to 1 over x plus 1, so you could also find that limit. And actually, if you found that limit, I should realize that if I just think of this as a simplified version, that's a hyperbola. And what's the asymptote of this hyperbola? Well, there's a plus 0. So I can write that down without any working. So you can work with the simplified version or the original version, it doesn't matter. Just to show you why this works out, if I divide the top and the bottom by x squared, this becomes the limit as x tends to infinity of 1 over x, which will tend to 0, 3 over x squared tends to 0. So basically that top all tends to 0. And the bottom will land up tending to 1, because the only thing that will be left is 1, and that is 0. And so that's why that occurred. However, I personally wouldn't have shown any of this working, because I would have simplified to realize it is a hyperbola, and I can figure out the asymptote of a hyperbola without doing any working. Great, 2 more to go. Let's have a look. Question F. F of x equals x minus 2 over 3x squared minus 11x minus 4. Always. Can use factorize and simplify. Now here I would probably start getting a bit lazy, and so I'd probably use my calculator to figure out if you can factorize the bottom. So don't forget you can solve that equation which figures out the factors for you. So these factors would have to be 3x. No one knows if these factors actually exist. I'm pretty sure this is minus 4 and plus 1. Pretty sure, because that'll be 3x squared minus 12x. Yep, it works out. If you want to use your calculator, you absolutely can. Now, this means you can factorize, but notice nothing simplifies. Now, you need to factorize anyway, because you need to see your vertical asymptotes. So it's never a waste to factorize. So my vertical asymptotes are at x is equal to negative 1/3 and x is equal to 4. I wouldn't bother actually showing how I got the negative 1/3. You just do it in your head from this factor. Okay, do I have any oblique or horizontal asymptotes? I absolutely have a horizontal, because that degree, the degree on the bottom, is bigger than the one on the top. I can also use my cheat in that because the degree on the bottom is bigger than the one on the top, I always know that my horizontal asymptote is going to be y is equal to 0. If this was my exam, I would show some working. So it's because it's the limit as x tends to infinity of x minus 2 over 3x squared minus 11x minus 4. I'm going to divide everything here by x squared, but that means if I divide the top by x squared, I get 1 over x, so that will tend to 0. 2 over x squared tends to 0, so the entire top tends to 0. The bottom is going to tend towards 3. So basically I get 0 over 3, which is 0. Great. Last one. Question G, h of x equals x plus 3 of x. Interesting question. Immediately I can see where their vertical asymptote is. It's at x is equal to 0 because I can see that x can't be 0. So I can immediately see there's a vertical asymptote at x equals 0. It's going to be quite fun to plot this because that's basically a hyperbola plus a straight line, which is pretty cool. Okay, now in order to work out horizontal or oblique, I'm actually going to combine these terms to 1. So if I make them 1 with a common denominator, this is actually x squared plus 3, which means I can see my vertical asymptote. I can see that I don't have a removal discontinuity, but I do have an oblique asymptote. And so how do I work out my oblique asymptote? I'm going to take x squared plus 3, and I have to rewrite it as x times something. Now, this is going to have to be x times x. That'll give me x squared. Now, I need to be accurate to the xth term. Now, so far, it's just x times x, which is x squared. Now, is that accurate to the xth term? Absolutely. So my remainder is plus 3. Now, that makes complete sense, really, because x squared plus 3 is equal to x squared plus 3. So that means I know my oblique asymptote is going to occur at y is equal to x. I also can see that my oblique asymptote and my graph will never hit each other because the remainder of 3 will never allow it to be equal to 0. And there we go. So hopefully we are feeling more comfortable with these asymptotes, and after practicing a little bit of an exercise, we can get on to actually drawing these functions, which is super fun. Okay, well done.